So we want to start thinking about geodesics more and the distances between geodesics as they move along a surface. Okay, so the first thing we want to do is to generalize polar coordinates to a general surface. These are called Gaussian polar coordinates. Let's remember. Let's begin with polar coordinates in Euclidean space on two-dimensional flat space, and I've indicated it here. I can parameterize my two-space with x and y in orthogonal directions. Okay, it's a flat space. I have a global sense of directions and global unit vectors, I and j, which don't vary. And then instead of using them, I can label my point x, y by the distance from the origin, okay, and the angle off the x-axis. So I've done that here. And everyone's familiar with that. X is equal to rho cosine phi, and y is equal to rho sine phi. Okay, the rays of fixed phi are geodesics, straight lines out of the origin, and then the circles are then called geodesic circles, right? These circles around here. So that's how I label my points. And of course, for lots of problems, okay, the polar coordinates are very handy indeed. And so we want to have a generalization to curved surfaces where the curvature is arbitrary. Okay. So how do I do that? Well, here I'll put such a polar coordinate system on my tangent plane. Okay, so I'm showing a curved surface here with a tangent plane, and the tangent plane is parameterized with rho and phi. Okay, but now I want to measure distances on the surface. Well, the tangent plane, of course, is the best possible approximation to the surface in the vicinity of a point P, okay, where it's tangent. But as I move away from P, of course, I know that I have deviations from Euclidean geometry, and it's those deviations that I want to study. Okay, so what I do to make Gaussian polar coordinates is that I think of this ray on the tangent plane as a bit of flexible rope. Okay, as a bit of flexible rope, and then I simply set up my Gaussian polar coordinates on the surface by letting the rope fall onto the surface, as shown. So I continue having a radial geodesic on S, okay, and the mapping that from the tangent plane to the surface itself preserves the distance. I just take the rope and let it fall onto S, maintaining the geodesic character of the radial when I do that. These are geodesic polar coordinates on S, okay, and we see how we've made them, and I like to think of it as just flexible ropes which are now put on it. And once I put the ropes on of a particular radius rho, then I come in and I make the generalization of the circles that existed on the tangent plane. Okay. So that's the setup, and these coordinates are particularly useful, and Gauss is very fond of them and use them in lots of situations. Of course, we've seen them before in the case of the sphere. This is just conventional polar coordinates, right? If you do conventional polar coordinates on S2, what do? Well, you measure the distance along a geodesic, along a great circle, starting at the North Pole, okay? Outer distance rho. Rho is related to the polar coordinate theta just by multiplying by the radius. The S2, the radius is 1, and so using S is the same thing as using theta. Okay, and then once I put out those geodesics spanning out in all directions, I then put a circle around here, okay, to measure the angle phi, okay, and so I have a simple set of polar coordinates that we know are very handy for parameterizing points on spheres. Okay, the geodesic circles of geodesic radius rho have circumferences which is just 2 pi r sine of rho over r, which is small, which of course is smaller than 2 pi r, and we've seen that indicates that the sphere has curvature, which is just 1 upon r squared, as we discussed when we did our spherical spaces early in the course, lecture 2. We'll come back to spherical, the geometry on spheres later, because we'll want to do it again, okay, and then contrast it with a discussion of hyperbolic geometry, which will be one of the goals of one of our special extra lectures. Okay, so that's how it works on a sphere. Back to the general case, we have Gaussian polar coordinates, and I've indicated them. Here, radial geodesics, and then we have these geodesic circles, the correspondence of varying phi on the sphere. And this is standard terminology. Now, why is this a useful coordinate system? Because the metric is very simple in these terms. E is now equal to 1 since the radial lines are geodesics. Okay, so if I write dr squared, then I'll have, for excursions in the rho direction, okay, just d rho squared. Okay, with no coefficient because of the definition of this line on the surface. In addition, f is equal to 0 since the geodesic circles are perpendicular to the radial geodesics as shown in the picture. Okay, and then the coefficient g, okay, inherits some properties from the existence of the tangent plane. In particular, when rho becomes very small, I know that g will approach rho as rho goes to 0, and we approach the tangent plane. So I know lots about the general metric already. It's nicely parametrized. Okay. In particular, the square root of rho, that's the length. Rho itself is the length squared. This should go to 0 when rho goes to 0, and its gradient should go to 1 when rho goes to 0. That's just the statement, okay, that the tangent plane becomes a perfect approximation of the surface when rho goes to 0. In that case, square root of g has to go to a rho itself, and so I express that statement through these two. That square root of g goes like rho, so it goes to 0 when rho goes to 0. Okay, and its gradient in the rho direction approaches 1 when rho goes to 0, because again, square root of g is really behaving like rho. Okay, so that's the situation. Now I can write down, for example, the Gaussian curvature, okay, in this language at the point P, because here we've had that E is equal to 1 and F is equal to 0. So looking back at the excellent theorem of Gauss, the expression for G reduces down to just minus, okay, the second derivative of the square root of g in the rho direction divided by the square root of g. I'm just going back to the expression that we derived, for the Gauss's excellent theorem, and we're putting in E equals 1 and F is equal to 0. Okay, so you see now I'm encapsulating all of the geometry in G. Okay, these two statements are rather trivial, just saying that when rho goes to 0, I go back to flat space, the tangent space. But now I want to look at the deviations from that, and I see that the deviations come in at the level of the second derivative, because that's where the curvature is. Okay. In fact, this gives us the triple derivative of g when rho goes to 0, because I can just differentiate this expression. Okay. So I solve for the second derivative of the square root of g and throw g and k on the other side of the expression. Then I differentiate that expression with respect to rho. Okay, so that gives me the third derivative of g, and when I differentiate the right-hand side, I get two terms which I've written out like this. I'm only interested in things when rho is small. What's the geometry in the vicinity of the point P, and how do I parameterize it? Well, when rho goes to 0, okay, then I have these two identities playing out for me. So this term goes away, and this coefficient goes to 1. So here's another expression for the Gaussian curvature. It's just minus, okay, the limit when rho goes to 0 of the third order derivative of the square root of g. Okay, so now you see I can study my metric and my intrinsic geometry in the vicinity of the point P. I'll just take the square root of g and Taylor expand it for small rho. Okay, so that's what I've done here. I've written it out for general angle, okay, but for rho going to 0. So here's rho of 0, here's the first order change, second order change, and third order change. And now I just evaluate everything. Here's square root of g at rho is equal to 0. Well, that's 0, goes away. Okay, here's this term with the first derivative of the square root of g in the rho direction at the point rho equals 0. That's just 1. So I get this term here. Well, I certainly expect that term there because that's the basis of polar coordinates. And then, okay, and then proceeding up here, I have this second order derivative. Okay, from theorem of Grecium, that's square root of g times k. But when rho goes to 0, square root of g goes to 0, so that term disappears, and I'm left with the third order deviation. Okay, which I see is just minus 1/6 from the Taylor expansion, rho cubed times k. Okay, and so there's my metric. Okay, and I've written out the metric for small rho. Okay, but it's written out far enough in accuracy, so I see my deviations from Euclidean geometry, and they're all encapsulated by one parameter of the surface, the Gaussian curvature, at the origin of my Gaussian polar coordinate system. Okay, so now I can do some calculations in this more rigorous formal setting that I illustrated before for the sphere. In particular, I can look at the circumference of the geodesic circle around the point P. Okay, so here's the circumference. Okay, I'm considering just line elements where the angle varies from 0 to 2 pi. I'm at fixed rho. Okay, and so I can substitute in my square root of g. Okay, from my Taylor series expansion here. Integrate things for the angle going from 0 to 2 pi. There's no angular dependence here, so I just get 2 pi from that. Okay, and then I can simply solve for k in terms of the circumference, and I find, okay, that k of p is equal to, okay, some coefficients, and the important point here being in the numerator, that it's the deviation of the Euclidean statement that the circumference is 2 pi times the radius that gives me the curvature. Well, you know, we anticipated this kind of a result when we were discussing spheres, but now we're doing it for a general surface. And as soon as we learn from the general analysis that the first deviations from Euclidean geometry for a general surface are encapsulated just by the curvature at the point P, we see that our little discussion on the sphere was really good enough. It was completely defensible, and and now we have another expression, another geometric interpretation of the Gaussian curvature, one that we're quite happy with. So, for example, k is positive if the circumference is less than the Euclidean result, and k is I'm sorry, and k is negative. This should be a negative here if the result goes in the other direction. If the circumference goes faster than the Euclidean result. Okay, so that's sensible. Okay, so we can take a moment and develop this a little bit more. This parameterization of the metric also gives us insight into what we were studying before as geodesic deviation, which we studied for the special geometry of the sphere. Now we can come back to it, okay, and ask the question, well, how quickly do geodesics deviate from one another as we move from an intersection point, away. Okay, here I've shown the geodesics in my Gaussian polar coordinate system, and then I've indicated a direction perpendicular to them, and I've indicated a field, J, which indicates the rate at which these geodesics deviate from one another, and I call it J for Jacobi. The equation for K in Gaussian polar coordinates is a step in the general direction of getting an equation for a Gaussian deviation. Okay, because I'll just write down the theorem, the excellent theorem. Okay, for this particular application. Okay, and I see it tells me what I'm interested in, how quickly the geodesic deviation grows as I move away from rho. The second order derivative of it grows and is controlled by the product of k and the square root of g. So this will prove to be a simple example of a Jacobi differential equation. We'll get the general case when we study holonomy. Okay. So I might consider lengths along segments of the geodesic circles. Right? So instead of doing the integral now in the theta direction from 0 to pi, I'll just do it from one geodesic to another geodesic, from theta 0 to theta 1, and then that's an easy integral to do, of course. And here's the result. And I see that then the distance along those geodesic circles, like this distance along here, okay, grows with rho, but the rate at which it grows is dependent upon the curvature. Okay, there's the common term that it grows to linear order as rho. Okay, that's the expected thing from Euclid. And then there's the correction. And I see that L of rho grows faster than the Euclidean case when k is negative, if I'm on a saddle, and it grows slower if k is positive, if I'm on a sphere. Okay. And we saw that in the case of the sphere already. This just generalizes some of the exercises that we did for special cases before, and now we see how to phrase it and generalize it to a general surface where k can vary from one point to the other. Okay, and that'll be an introduction to the idea of geodesic deviation. Okay, it's a very important concept in general relativity. Okay, so that's all we'll do with that subject for the time being. We'll come back to some of it later, but now we want to reconsider parallel transport and holonomy in a more general framework. So that's what we'll turn to next time.